Roughly 4.5 billion years ago, the early Earth experienced the Iron Catastrophe, a runaway gravitational collapse triggered by intense internal heat. Dense liquid metals like iron and nickel sank toward the planet's center to form the core, displacing lighter silicates upward to form the mantle. This reorganization of elements sequestered siderophile, or iron-loving elements, deep into the core. This left the remaining bulk silicate Earth depleted in heavy metals like ruthenium and molybdenum, which effectively locked the planet's primary chemical inventory. Shortly after this differentiation, the planet's surface cooled. We can see evidence of this in Hadean zircons, tiny, resilient crystals formed between 4.4 and 4.0 billion years ago, which provide a record of the earliest crust. These zircons possess specific oxygen isotope ratios and mineral inclusions that only form through interactions with liquid water. Their existence confirms that a solid crust and surface water were present on the Earth immediately following the formation of its core. This combination of extreme metal depletion and early surface water creates a strict geochemical boundary condition. Any model for Earth's formation must explain how these two distinct states could exist so early in the planet's history. To explain the presence of surface water and trace heavy metals on a differentiated planet, researchers have traditionally turned to models of heterogeneous accretion. The central assumption here is that Earth required a late delivery of material. These models suggest the planet accreted between 6% and 40% of its total mass from water-rich carbonaceous chondrite bodies migrating inward from the outer solar system. However, recent Bayesian latent factor analysis by Saucy and Bauer reveals a mathematical discrepancy in this delivery model. By analyzing 10 distinct isotopic systems simultaneously, the researchers could test the probability of this outer system contribution. While previous studies often relied on 1 or 2 isotopic markers, examining 10 systems at once creates a much narrower range of possible outcomes for Earth's origins. This multivariate approach suggests a different narrative, that Earth does not represent a mixture of distant reservoirs, but is instead a homogeneous end member of the inner solar system. The foundation of this analysis is the isotopic dichotomy, which divides all known primitive meteorites into 2 distinct genetic reservoirs, the carbonaceous group from the outer solar system and the non-carbonaceous group from the inner system. Because older models used smaller datasets, often focusing only on chromium-54 and titanium-50, Earth appeared to sit in a position explained as a hybrid mixture of these 2 reservoirs. Mapping these reservoirs across 10 elemental systems isolates carbonaceous and non-carbonaceous meteorites into 2 clusters. Within the inner system, a chondrite subgroup forms a linear baseline. Earth falls exactly on this regression line, anchoring the inner system trend rather than deviating toward the carbonaceous cluster. Geometrically, this indicates that the bulk silicate Earth is a direct extension of the inner solar system array, rather than a combination of different sources. The siderophile mass balance, locked in during the Iron Catastrophe, constrains the amount of material Earth could have accepted from the outer solar system. Because elements like ruthenium and molybdenum were almost entirely removed by the forming core, the tiny amounts remaining in the mantle are extremely sensitive to any later additions. Their isotopic signatures function as a high-fidelity record of late accretion. Simulating the addition of just a 0.1% mass fraction of carbonaceous chondrite material to Earth's mantle yields immediate results. This tiny addition shifts the ruthenium value far outside observed error bars. The mantle cannot accommodate even a fraction of a percent of outer system material. This constraint applies to other systems as well. For refractory elements like calcium, adding just 2% of outer system material would shift the isotopic budget beyond what we actually measure in Earth's rocks. This plot compares the observed isotopic composition of the bulk silicate Earth against a modeled composition based purely on the inner system trend. Across all element categories, observed Earth data locks onto this diagonal line. Predicted values match real-world measurements with high precision. These mass balance constraints indicate Earth's composition is a natural result of local accretion. There is no mathematical requirement for missing components or additional outer system delivery. These findings support a model of homogeneous accretion, where the material gathering to form the Earth maintained a consistent nucleosynthetic signature throughout the core formation process. This complex data can be simplified by collapsing the 10-isotope latent factor plot into a single one-dimensional axis called isotopic Euclidean distance. On this axis, we can map the known terrestrial bodies. Earth sits at 0, Mars at 0.69, and the asteroid Fresta at 1.55. This isotopic distance correlates strongly with the physical distance these bodies sit from the Sun. The building blocks of the inner planets were organized according to their position in the early disk. Isotopic signatures in the early solar system followed a measurable spatial gradient, which allowed planets to form from a uniform local supply of material. We also see that planetary mass in the inner solar system follows a Gaussian distribution, with the highest concentration of mass centered near 0.9 astronomical units. By fitting a mass-conserving curve to the isotopic distances of Earth and Mars, we can project the composition of unsampled planets. Based on their masses, a model predicts the isotopic coordinates for Venus and Mercury. Both sit on the far tail of the distribution. This suggests that Venus and the planet Mercury are even more extreme isotopic end members of this inner system gradient than Earth is. When we combine this unified inner disk gradient with the evidence from Hadean zircons, the narrative of Earth's origin changes. The inner solar system natively contained the full chemical inventory required to build a habitable, geologically active Earth, with no interference from the outer system required.